EOQ with backordering. In this model, again, we relax only one assumption with respect to the basic EOQ model, and that is that backordering in the basic EOQ model is not permitted. Here, backordering is permitted. All the other assumptions remain the same. So our schematic now looks like this. Here we have on-hand inventory. The on-hand inventory depletes at a constant rate of demand D. It reaches 0 at this point of time. But here, no replenishment arrives as in the basic EOQ model. Rather, the organization decides to allow back ordering, and it takes back orders. So you can see that the level of back order is building up here. So here in the schematic, it is shown as if inventory is becoming negative. Inventory cannot become negative. Physical goods cannot take a negative value. So what is happening is that this just represents the existence of back orders. So in our book, we show as if the inventory is negative. So back orders are building up and they reach a maximum level. So the system has been planned in such a way that an order is placed at a certain point when the level of back orders has reached some value, and after the lead time elapses, the replenishment arrives. So when the level of back orders reaches the value B max, the replenishment arrives. The quantity ordered is such that all the back orders are wiped out and a certain level of on-hand inventory is built up, which is Q max. So as in the basic EOQ model, we assume that the same quantity Q is ordered each time, and the level of inventory reaches a maximum called Q max and alternates between Q max and 0. The on-hand inventory goes between Q max and 0 and remains 0 for some time when the back orders are building up. So when will this apply in real life? There are situations when the item that is being sold is very expensive, like high-end TV sets, or say diesel generators, or you can think of heavy machinery. So there are certain goods which are expensive to store and hold, and holding costs are high if the dealer or the retailer wants to keep them in stock. And the customer is willing to wait. A basic condition for backordering system to work is that the customer is willing to wait, or the customer has no choice but to wait. There are no competitors who offer the same item that the customer can easily access, and therefore the customer has to wait. So in situations like that, backordering works, and the backordering cost in the basic EOQ model, the backordering cost is infinity. When we say backordering is not permitted, it's as good as saying that the backordering cost is infinity. Here, backordering cost is not infinity, it is some finite number, and often the backordering cost is less than the holding cost. The holding cost is so high that the option of backordering looks attractive, and the customers are willing to wait and accept the item after some time after they place the order. Okay, so with this schematic, we will see that the quantity ordered Q is Q max plus B max. So B max is this length, the length of the line segment here, which the whole line segment represents the ordered quantity Q. This portion of the line segment represents B max, and this portion represents Q max. So Q is equal to Q max plus B max. P is the proportion of time on-hand inventory is 0. Or you can see in this graph here that the cycle, the order cycle, the replenishment cycle is divided into two parts. In one part, which represents the existence of on-hand inventory, that part takes place over a period of time which is 1 minus P proportion. And the P proportion of the time, there is no inventory on hand, or there is back ordering. Okay, so P represents the proportion of time that back ordering happens, or on-hand inventory equal to 0, and 1 minus P is the other proportion of time of the cycle when it is greater than 0. Okay. Now with this, we move forward and we write these equations. The maximum inventory level Q max is Q into 1 minus P, and the average inventory level Q average is calculated over the entire cycle, where in the 1 minus P proportion of the cycle, it is Q max by 2, and in the remaining P proportion of the cycle, when there is no on-hand inventory, it becomes 0, and therefore the average over a full cycle will be Q max by 2 into 1 minus P plus 0 into P, right? So since Q max itself is Q into 1 minus P, the Q average will become Q by 2 into 1 minus P, the whole square. Okay, similarly, so the maximum back order level B max is Q into P, and the average backorder level will again have a similar structure like that of the average on-hand inventory level. Will be Bmax by 2 into P plus 0 into 1 minus P, and this will finally reduce to Q by 2 into P square. So the cost of holding CH becomes Q by 2 into 1 minus P the whole square into small ch. The cost of backordering, capital CB, becomes Q by 2 into P square into small cb, where the small cb, just like small ch, is expressed as cost per unit per time for backordering. Per unit backordered, per unit time for which the backordering happens. That cost is called small cb. And CO is unaffected by both these things. It remains the same as what it was in the basic EOQ model. That's d by q into small co. So the total cost function looks like this. Capital C equal to Q by 2 into 1 minus P square into CH plus Q by 2 into P square into CB plus D by Q into CO. Okay. Now, if you look at this equation, there are actually two unknowns. We don't know beforehand what the best P should be, the proportion of time that backordering happens. We don't have, we don't make an assumption regarding that. We allow the mathematics to tell us what the best P should be, just like we are looking for the best Q. So here in this equation, both Q and P are unknowns for us. So if we have to optimize C with respect to optimize C, then we have to optimize it with respect to both Q and P. There are two unknowns here, or two variables. So to find the optimal order quantity Q and the proportion P, we take partial derivatives and set them equal to separately equal to 0. So the first partial derivative is with respect to P, the proportion P, and the second one with respect to the Q, order quantity Q. So you get two equations in one each in P and Q, both in P and Q. So the first equation is this: when you take the first derivative with respect to P, it will be minus 1 minus P into CH into Q plus P into CB into Q equal to 0. And this, when you rearrange, yields P star, the optimal proportion of time that backordering should happen, as equal to CH divided by CH plus CB. And you can see that from this you can also calculate 1 minus P star, which is the proportion of time that on-hand inventory will exist. And that will be CB divided by CH plus CB. Okay. The second partial derivative, dou C by dou Q equal to 0, will give us 1 minus P the whole square divided by 2 into CH plus P square by 2 into CB minus D by Q square into CO equal to 0. And this leads to Q star is equal to square root of 2dCO divided by 1 minus P star square CH plus P star square CB. Okay, now you get an expression for Q star, but then this expression for Q star has P star inside it, right? So therefore, to remove P star, we have to substitute the expression for P star that we obtained earlier. So we get this expression. So this becomes simpler than what we had earlier. Q star is square root of 2dCO into square root of 1 by CH plus 1 by CB. Now, if you reflect on this formula right away and compare it to the basic EOQ formula, the basic EOQ formula was just Q star equal to square root of 2dCO into square root of 1 by CH. So now, this factor 1 by CH has been replaced with 1 by CH plus 1 by CB. So essentially what's happening is that the holding cost, which was incurred in the basic EOQ model, is now shared by both holding and backordering. The remaining portion of the formula, 2dCO square root, remains the same. Okay, going forward, we can see that the same formula can be represented in three different forms. The original form that we got, Q star equal to square root of 2dCO into square root of 1 by CH plus 1 by CB. This can be rewritten as this, square root of 2dCO by CH into square root of 1 plus CH by CB, or as this, Q star equal to square root of 2dCO by CB into square root of 1 plus CB by CH. Okay, so all three of them are equivalent. They are the same formula written in three different ways. Now, the reason for writing them in three different ways is because these different ways help us to derive different interpretations, which we will see as we go forward. Okay, first, let's look at the maximum levels. Q star max is Q star into 1 minus P star. This was the formula we started out with. And this reduces to this formula in terms of D, CO, CH, and CB. Similarly, B star max is Q star into P star, which reduces to this formula. So you can see that the difference between these two formulae essentially is in the second term. The first term is the same. The second terms are inverse of each other. So what is the implication? Reflecting on these formulae, let's take a scenario when the holding costs are low and the back ordering costs are very high. Okay, so we're taking now two extreme scenarios. In the first extreme scenario, we take CB, the back ordering cost, to be much, much higher than the holding cost. CB is much, much greater than CH. Okay, then what will happen? You look at the Q max formula to answer this. The Q star max formula tells us that it will tend towards Q star. So when CB is much, much greater than CH, you apply that here, you'll find that in that limit, Q star max tends towards Q star, which tends towards square root of 2D CO by CH. And your B star max tends towards 0. Okay, so you can apply this condition CB much, much greater than CH. Okay, you can say if CB is infinitely greater than CH, or CB by CH tends towards infinity. So when that happens, these results will appear, which essentially means that our system is tending towards that of the basic EOQ model, having only holding cost and no back ordering cost. And this would be the case when we are dealing with goods which are low valued and fast moving like FMCG or inexpensive electronic items and so on. Now the other extreme scenario is when the holding costs are very high and the back ordering costs are very low. This is what we are interested in by creating this model. So here CH is much, much greater than CB. In that case, what would happen? The Q star max will tend towards 0 and the B star max will tend towards Q star, the exact opposite of the previous scenario. And that would tend towards square root of 2dCO by CV. Okay, so it's as if we are inverting the basic EOQ model or replacing the basic EOQ model's holding cost with the back ordering cost. It's as simple. CH is now replaced by CB in the basic EOQ model. So this is basically tending towards a situation of pure back ordering with no holding at all. It's as if it's a make to order system. The item is supplied only after, item is acquired only after the customer places the order and then given to the customer. So this is analogous to the basic EOQ model in the sense that we are essentially replacing the CH in the denominator of the basic EOQ model with the CB. And when would this apply? Like we discussed earlier, when goods are very expensive, high valued and slow moving, or they're highly customized. And in all these cases, the customers are willing to wait for the good to be ready. And also in situations when even if the good is not high valued or slow moving, it's a condition in the market when there is only one supplier and there are no competitors, or the customer for some reason doesn't have access to the competitors, or the customer prefers to, even if there are competitors that are accessible to the customer prefers to go to only this particular supplier, and the customer is willing to wait for this supplier to acquire it. So in all these kind of cases, the back ordering model would be very relevant. Okay, now generally speaking, we are looking at a model in which both holding and back ordering happens simultaneously. We are not looking at necessarily at the two extremes. We are looking at the situation when there is back ordering for some time and holding for some time, a mix of the two. Okay, this is something that many suppliers might like to follow. Okay, so the formula for the holding cost turns out to be this, and this is got by replacing the formula for Q star and P star in the basic general equation. Similarly, the CB star formula and the optimal order cost CO star formula. So now you'll see that all these three are different from each other, but interestingly, you'll see that CH star plus CB star adds up to CO star. Okay, so in the earlier two models that we saw, that of the basic EOQ and the one with the gradual replenishment, in those cases we saw that the holding cost was equal to the order cost at optimality. But here we see that the holding cost plus the back order cost is equal to the order cost. And this again lends support to our insight that the holding cost and the back ordering cost are complementing each other in this situation. The total optimal inventory cost will be this formula. It will be the sum of all these costs, or you can say twice the order cost. And so again here the realization is that the optimal solution, the order cost as before, accounts for half of the total inventory cost as in the other two models. The other half is split between the holding cost CH star and the back ordering cost CB star, and not split equally, it's split in the ratio of CB is to CH. Right? So CH star by CB star is equal to small cb by small ch. Okay, now coming to the time between orders, the optimal time between orders, T star will be Q star by D, the cycle time, and this turns out to be this formula. Again, you will see a similarity with the basic EOQ formula. It's the basic EOQ formula multiplied by a factor of square root of sorry, in the basic EOQ formula, we had only CH in the denominator, and that is replaced by square root of 1 by CH plus 1 by CB. Okay, the duration of time backordering happens within an order cycle will be given by this formula. It is simply the T star multiplied by P star. Okay, that is how we defined P star. P star is defined as a proportion of time that the backordering exists in the system. And therefore, just taking T star and multiplying it with P star will tell us the duration of time over which in a given cycle the backordering will happen. And this also is the maximum time that a customer needs to wait after ordering to receive the good. Okay, so when there is back ordering, customers are giving back orders, customers are placing orders, not all at the same point of time, they're all placing orders over an entire time period during which the back ordering happens. And therefore, not all of them have to wait for the same amount of time. The maximum amount of time is given by this amount, the customer who ordered the earliest among these customers who ordered when there was back ordering. Okay. Likewise, we can also talk about the duration of time that inventory is on hand within the order cycle. And this is nothing but T star into 1 minus P star. And this is the maximum continuous time that the store can fulfill an order when it arises without asking the customer to wait. Okay, so the on-hand inventory has just come. The replenishment has just happened. So from that point of time till the back ordering begins, that is the duration of time mentioned here. And if a customer comes at that point of time, then he will definitely get it. Or for how much more time will the customers get without having to wait? That is given by this time. Okay, now let's do another example. So we have a remotely located small town. Okay, so you can think that this is a small town with very few facilities and a very small market. So Mehta Electronics, there is a big electronic shop which sells large screen, high definition TV sets, the expensive ones that you see in these stores, and which very often we think we should have one in our house, but it's too expensive for us. Apart from this shop, there is only one other shop that sometimes stocks the same items. The TV sets are valued at rupees 1,20,000 each, and they are sold at 1,56,000. The annual holding cost is taken as 30% of the unit value. So we can compute the holding cost per unit time. The order cost is rupees 7,500, and the annual demand for the item is estimated to be, this number is 60 units. Okay. Mehta Electronics decides to follow the EOQ model. How much should it order, or how many units should it order in a given replenishment cycle, and how many times a year should it order? What are its total inventory costs? So with the basic EOQ model, you can compute all these. Okay, now since the town is remotely located, customers are accustomed to wait for a while to get a product they want. Hence, the shop is exploring whether it can switch to a back ordering model and reduce its inventory costs. So taking into account the various options that customers have and the maximum that they might be willing to wait, Mehta assesses the back ordering cost to be rupees 12,000 per unit per year. If Mehta were to implement this back ordering idea, what will its optimal back ordering time proportion be? What will the maximum back order level be? By how much will the maximum on-hand inventory reduce? And what will the optimal inventory costs now become? Finally, what is the maximum time that a customer has to wait for the TV set? Okay, so think over this, answer these questions, and then take the video forward to see what answers I have got. Okay, so these are my answers. So this is in this portion, you are given the basic data. The demand rate is taken as 60 units per year. The holding cost turns out to be 36,000 rupees per unit per year. The cost of ordering is 7,500. The back ordering cost, when the back ordering model is followed, is 12,000 per unit per year. So by applying the back ordering formulae, we get that the proportion of time, the optimal proportion of time that back ordering should happen is 0.75. And the opposite, when the on-hand inventory exists, is 0.25 proportion of time. And this 1 by 1 minus P star was computed just to make it easy for applying some of the formulae which have this in their factor. Okay, now these results emerge, and as before, the first column has the inventory measures, output measures. The second column has the outputs connected to the basic EOQ model, which is currently being followed by Mehta Electronics. And if Mehta Electronics were to follow the back ordering model, what would they get? That is given in this column. And the change percentage is given here in the last column. Okay, so we see that the order quantity essentially doubles. It goes from 5 to 10. So if you switch from the basic EOQ model to the back ordering model, the order quantity increases, and here you can see it's doubling. We saw that in the gradual replenishment model too, it was increasing. So it increases. The maximum inventory level reached now comes down. In this case, it has become 50%. And there is back ordering. Earlier, there was no back ordering. Now there is a certain level of back order. The average inventory levels naturally will come down, and you can see that it has gone down drastically here in this example. It was earlier 2.5 units, but now it has come down to 0.31 units. This is the time average level of on-hand inventory. So it has gone down by 87.5%. Okay, and there is now an average back order level that is given by this figure. Earlier it was not there at all. Now this is how the inventory costs have changed. You can see that the holding cost, it was earlier 90,000 rupees per year, and that has come down to 11,000 rupees, 11,250 to be precise. Now there is a back ordering cost incurred. There was no back ordering cost earlier. The order cost has come down from 90,000 rupees to 45,000 rupees. Even though demand is the same, we are ordering double the quantity now, right? So which means our number of orders in a year will come down, become half, and therefore our ordering cost has also become half. And we see, interestingly, that the total inventory cost has also become half. It was 1,80,000 per year earlier. It has now become 90,000 per year. So by switching from the basic EOQ approach to the back ordering approach, we're actually able to save money. So I've also made these notes. You can see that here also we observe that CO star is CH star plus CB star, as we saw in the formulae. The inventory cost halves. Maximum wait time for the customer after ordering is given by this number, 1.5 months. The customer now may have to wait for as much as 1.5 months. Of course, all customers don't have to wait this long. The customers who are ordering very close to the time of replenishment, their back ordering or their waiting time will be much less. But the customer who orders immediately after back ordering begins may have to wait for 1.5 months. Of course, when this model is applied in real life, the supplier who is applying the model will take that into account, whether customers are willing to wait for that long. And accordingly, keeping that into account, the back ordering cost is calculated. Right? If customers are not willing to wait that long, then this model cannot be applied. The back ordering cost accordingly should be made higher. The higher the back ordering cost, the lower will be this wait time, the maximum wait time. Right? So, when you take the model from a real, from this mathematical, from what we see here with the mathematics to the real life situation, we have to apply it with appropriate caution or appropriate wisdom. So this ends our discussion on the EOQ with back ordering model.